Hello everybody, my name is Ben Jones and today I will be presenting the work I did this summer, Transformers for Tabular Data Fusion. I was mentored by Dr. Nick Gasolfi, Emma Erickson, and Dr. Artur Dubrowski in the Auton Lab. So to give a little background, a little motivation for this problem, we're in a distributed setting and data can vary from one data silo to the other. It could be due to different ecosystems, conflicting interests. The example I always like to bring up is healthcare. These different hospital systems will have different ways of tracking patient data that may not always be consistent with one another. Um, and if you desire to combine or merge some of this data together, that will lead you down the path of extensive feature engineering, data cleaning to get this data into one place. And also the features may be very similar to one another, but not exactly the same. The example I have there, under 21, may be a feature in one data set and is adult is a feature in another. And they may hold very similar information, but because the feature names aren't exact or uh, other scenarios may arise, they'll be unable to be merged, and even a human may not pick up on that, especially if the feature names aren't as descriptive. Utilizing these individual models from the individual data silos for inference of other silo data, it might be just not feasible because the distributions may be different from silo to silo. So what are the goals to solve some of these problems that I mentioned? Well, we want to resolve this feature difference without tailoring our model to specific types of data. So we don't want to necessarily train on each individual silo's data. We want a unified solution that works for any type of uh, data type. We want to demonstrate this proposed resolution can be used for good performant models. In the end, we want information to be successfully extracted out of whatever our model outputs. And we want to eliminate or at least reduce the need for this extensive feature engineering uh, to a specific use case. So our approach, we want to abstract away these semantic differences in all these data silos so we can combine all of them into one through this abstraction. So the first step is actually to run a feature linkage algorithm to detect similar feature representations across these silos. And that is because some features may be common across all silos, and we want to identify those and bring those into uh, our end result, concatenated data in this case, without any transformations at all. And so our feature linkage algorithm will automatically go in and identify either exact matches across all silos or very, very um, similar features by their names or by their distributions. And that is all done without human intervention. All the human has to do is choose the number of features to be linked by that algorithm. And then the rest of the features that do not get linked are fed into a sentence transformer, and I'll talk about that in a little bit. And the sentence transformer, again, they put all the data records into this latent vector space where they can all be successfully combined, and they are concatenated at the end, those embeddings, with the features that were linked. And now we can train a model on this end concatenated data. So how do we do this in specifics? Feature linkage, we define two anchor datasets. So in this case would be the two ones in blue. Could be arbitrary number of datasets. It has to be greater than or equal to 2, of course. And an arbitrary number of features for each of the datasets. So once we identify a pair that either is an exact match or they're very similar in the two anchor datasets, we take that pair, we take one of the elements, and we compare it against all of the other sets of features from all of the other data silos. And we do this because computing all of these similarities, the cosine similarities in this case, with all of the data silos simultaneously is very costly, computationally expensive. So in order to reduce the number of comparisons we need to make, we first identify a similar pair in the first two data sets, and then we just use that individual pair to compare against the rest of the features instead of comparing all of the features in one silo to all the features in all the other silos at once. It's a lot of computation, and this just helps to speed up uh, the feature linkage algorithm greatly. Uh, we have a couple different encoding strategies. So this step is where we take the unlinked features and we feed them into the sentence transformer. Obviously, you can't take raw data records and feed it into a sentence transformer. It needs to be in a sentence format. So there are a couple different ways that we tried encoding these individual data records into sentence formats. There's a standard way, you just insert um, a space between the feature name and the value. You can have an equal sign, or even more, coercing it into a sentence format, you insert an is in between the name and the value for that feature. So some of the results that we got from our experiments, we used a custom multi-layer perceptron classifier. Some of the details like batch size and learning rate are in the paper. And what we found was that it was actually wasn't what we were expecting, but our pipeline kind of identified perceived harder or more difficult problems because for some of the problems, like this income classification task, the pipeline was able to, or the model was able to successfully extract the information that it needed um, from the pipeline's result. And as you can see, it achieved good accuracy. The green line is the linked features only, so that's pretty intuitive. Those are only tabular features. As the number of features you add to the model increases, the model performance increases. Um, but the embeddings only model really surprised us because it was able to extract virtually the same information as it would from, hypothetically speaking, if all of the data silos had the same schema. If a model was trained on that unified data set, that would be the performance that you expect. But in other tasks, it was barely beating baseline, um, and even extensive feature engineering, data mining really couldn't get a unified model uh, that performance to increase. So it's maybe for future work, but it goes to show that maybe this could be used in identifying how much work needs to be put into a certain data set or data sets in order to produce a model that is deemed effective. But all in all, this fusion model can adapt to a wide number of data sets, tasks, and it produces desirable performance. Uh, this image classification task as well demonstrates that a little bit. This is We were trying to discern the difference between the types of encoding strategies here. There was no feature linkage here. It was all the same dataset. Uh, but as you can see, there's really no significant difference between the three encoding strategies that we used. Um, and yeah, still, all of the embedding only models are performing well above the baseline. This was a 7-class image classification task. So what can we conclude from this work? The end model can actually extract useful information out of the pipeline result. This feature linkage algorithm allows for more effective joins, and it's pretty hardy to string transformations, uppercase, lowercase. Uh, some methods use string metrics. Um, so it gets a little bit more information. It gets the semantic meaning of the feature instead of just the characters in the feature name. The type of encoding strategy really has little to no effect on the end model's performance, and the human selecting the number of features to link grants more control over this fusion process, um, which is really nice for the end user. I would like to thank a couple people, uh, Rachel, Morgan, Dr. Dolan. Thank you for allowing me to do research this summer and facilitating all the events that happened. The Auton Lab, Emma, Nick, Archer have been a massive, massive help in this and fantastic mentors. And then thank you to my buddy Shashwat for looking over my poster. Uh, so thank you very much.